In today's lesson, we're going to be talking about antidifferentiation. In our past lessons, we've been talking a lot about derivatives and doing differentiation. Whenever we take the derivative of a function, say we had the function x squared. The derivative of this function, denoted as d dx, the derivative with respect to x, of x squared is equal to 2x by the power rule. But what if I told you that this was the derivative of the function and I want you to find what the original function was? That's where antidifferentiation comes into play. Let's talk about it. So before we go into examples and how to antidifferentiate, let's talk about exactly what an antiderivative should look like. Say we had a function capital F. This function capital F is the antiderivative of the function lowercase f if the derivative of the capital F function is equal to f of x, its derivative. So let's say our function was x squared. We just talked about this a second ago. We know the derivative of this function is 2x. And since the derivative of x squared is equal to 2x, we know that 2x is equal to 2x, which means that this function, x squared, is the antiderivative of 2x. In other words, we're working backwards from where we were before. Instead of taking the original function and finding the derivative, we are given the derivative and have to find the original function. Let's go over some notation real quick. If we want to take the antiderivative of a function, say 2x like we've been using this whole time, if we wanted to find the derivative of this function, we would write as d dx. This would be the notation, and this derivative would equal 2. But in this case, we're trying to find the antiderivative. We can notate that with this very elongated s. This is the antiderivative symbol. If we put this elongated s next to our function, that means we need to find the antiderivative of it. We also tack on dx here, or d whatever variable we have here. So say our variable was 2z, we would put 2z dz instead of 2x. It's just like derivatives where we want to take the derivative or the antiderivative with respect to a variable. And of course, as I've told you, the antiderivative of 2x is equal to x squared. So this is what the notation would look like. In more general terms, f prime of x, remember f prime is just another way to say the derivative of a function, f prime of x dx is equal to f of x, the original function. This is the most general way to write our notation. I also want to emphasize something very important. Whenever you're taking the antiderivative, you have to add a plus c to the end. Remember, whenever you take the derivative of a constant, it just turns into 0. So if you were to take the antiderivative of a function, say 2x, the derivative of x squared plus 7 is still just 2x, but we don't have the plus 7 added to it. Because remember, the derivative of a constant is always 0. So we just had to add this plus c because we don't know if there was a constant there or not. No matter what antiderivative you do, you add a plus c, except for one case which we'll get into in a future lesson. For now, just write plus c at the end of all of your antiderivative questions. Okay, just like with derivatives, let's talk about some basic rules for antidifferentiation, how we can solve these problems. Say we had the antiderivative of c, a constant, times f of x dx. If we have a constant being multiplied by the entire function, we can pull it out to the front like this and change this function into c times the antiderivative of our function f of x dx. These two are equivalent, and sometimes whenever you take your constant out from the front, it makes your antiderivative much easier to solve. Now remember, when we were learning about limits, we could also take constants out to the front. It's the same concept here with antiderivatives. Our next rule, say we had something like this. Say we had the antiderivative of f of x plus g of x dx. We can split this by the addition sign to change this into the antiderivative of f of x dx plus the antiderivative of g of x dx. This also applies for subtraction. We can split our antiderivatives by addition and subtraction, just like with derivatives and limits. If we can split our functions by addition or subtraction, it can usually give us two much more easy functions to take the antiderivative of instead of one more complex function. Rule number 3. Say we want to take the antiderivative of x to some power dx. Some power being notated by n. That could be x to the second power, x squared, x to the third power, x cubed, x to the fourth, fifth, so on and so forth. Similarly to the power rule from derivatives, we have a power rule for antiderivatives. If we want to find the antiderivative of a function to a power, all we do is take our variable, then take its original power, add 1 to it, and then divide that by whatever that new power is, n plus 1. For example, if we wanted to take the antiderivative of x squared dx, all we would have to do is take x to the 2 plus 1 power, n is equal to 2 in this case, and divide that by 2 plus 1, giving us the antiderivative of x cubed divided by 3. It's a very simple concept, but very, very important, and you get more used to it the more you do it. And then the last simple antiderivative rule is one that's very similar to derivatives. If we want to take the antiderivative of e to the x dx, this is just equal to e to the x. Remember, whenever we took the derivative of e to the x, it just equaled e to the x. Well, it turns out if you go backwards, you get the same thing. This is by far the easiest one to remember. Let's say we wanted to find the antiderivative of x squared plus 4x cubed dx. What would that equal? Well, there's two things we can do here. One, we have this addition sign that we can split by, so let's do that first. Let's change this into the antiderivative of x squared dx plus the antiderivative of 4x cubed dx. Now we also have a constant being multiplied by our entire function. So let's pull that 4 out to the front and change our function into this. Now we have x squared dx, the antiderivative of x squared dx, plus 4 times the antiderivative of x cubed dx. Now the last step here is just to use the power rule in order to solve both of these antiderivatives. Let's use the power rule on our first antiderivative first. We get x to the 2, that's our n value, plus 1 power divided by 2 plus 1, plus 4, and then once again we use the power rule here, 4 times x to the 3 plus 1 divided by 3 plus 1. Simplifying this down a bit, we get x cubed divided by 3 plus 4 times x to the 4th divided by 4. You may notice that we have a 4 that would be on top and a 4 on bottom, so these two cancel out to just equal 1. So the antiderivative of x squared plus 4x cubed is equal to x cubed over 3 plus x to the 4th plus c. Do not forget your plus c. We don't know if there was a constant there. We need to add the plus c. Do not forget it. On your test, you will actually lose points. I have lost quite a few points in my past just from forgetting the plus c. And that's our antiderivative. That wasn't too bad, right? We're going to do a couple more examples so you get better and better at it. We're going to do our second example in red. Let's say we want to take the antiderivative of 3 divided by x dx. So what can we do here? It doesn't seem like there's anything really obvious, but I do want to draw your attention to this 3 on top. This is equal to 3 times 1 over x, which means that this 3 is a constant and we can pull it out to the front. So that changes our problem to 3 times the antiderivative of 1 divided by x dx. Now what function, when you took its derivative, equaled 1 divided by x? That's right, the natural log of x. So this is just 3 times natural log, or ln, of x plus c. Do not forget the plus c. I forgot it many times, and I don't want you to forget it. Don't forget the plus c. And that's it. That's our answer. Sometimes, like derivatives, these problems aren't all that difficult to solve. They're a little bit weird to get used to simply because you're going backwards instead of forwards like you're used to currently, but they're not too bad. Let's keep going with our example. Let's find the antiderivative of 5 times the square root of x dx. Now you may be a little bit confused because I didn't mention how to find the antiderivative of a square root function. And don't worry, it's not too hard. You may remember that the square root of a function is the same thing, so square root of x is actually equal to x to the 1/2 power. And that's a little bit easier for us to work with here in calculus. But you may also notice that this 5 is a constant being multiplied by a function, so we can pull this 5 out to the front. So this turns our problem into 5 times the antiderivative of the square root of x dx. Or as I just noted earlier, instead of making that square root of x, let's make that x to the 1/2 power because we have a rule that will easily solve this antiderivative. Let's use the power rule for antiderivatives. This now turns into 5 times x to the 1/2 plus 1 divided by 1/2 plus 1, and plus c. Do not forget your plus c. Now you could leave it in this form, but this looks kind of bad, so let's simplify it down a little bit. This is also equivalent to 5 times x to the 3/2 power divided by 3/2 plus c. And to finish off this problem, we need to multiply 5 times x to the 3/2 divided by 3/2. Remember, a constant is the same thing as its constant value divided by 1. Technically, this is a fraction. So this part here, this 5 divided by 3/2 here, is equivalent to 5 divided by 3/2. Now, a little algebra trick that you may have forgot about is in order to divide by a fraction, you can just multiply by its reciprocal. So this is actually equal to 5 times 2/3. The reciprocal, of course, being the numerator and denominator being flipped. 5 times 2/3 is just equal to 10/3. So this is equal to 10/3 times x to the 3/2 power plus c. And that's our antiderivative. That one took a little bit more algebra, but isn't terribly hard still. Like I said, you get a lot better at these and a lot faster at them the more you do them. So let's do yet another example. And this example is going to be a little bit longer, so bear with me, but it'll help you practice. Okay, in this example, we need to find the antiderivative of x to the 4th plus the 4th root of x plus 7 divided by x squared dx. Now, how can we make this function simpler? Because this is long and complex and very intimidating. Well, you may notice that we have addition signs splitting up every top function, which means we can turn this fraction into 3 smaller, but more importantly, simpler fractions that can help us solve this problem much more easily. So let's do that now. First, we're going to take x fourth divided by x squared, and we're going to draw that in blue. So that'll be here. Now we need the antiderivative of x to the 4th divided by x squared dx, plus, and now we need our middle function here, the 4th root of x. I'm going to draw that in green to differentiate these two. You like that calculus pun? Anyway, the 4th root of x is the same thing as x to the 1/4. So I'm going to write that here, still divided by x squared dx. And then we need to get 7 divided by x squared and make that its own antiderivative. So I'll denote that in red. It'll be plus 7 divided by x squared dx. Okay, let's simplify down these functions a little bit. We're going to do this first function and this third function, and then we'll come back to the middle one because that one's a little bit more complex. First, x to the 4th divided by x squared. We'll remove both powers here, but only remove 2 of the powers here. So this changes into the antiderivative of x squared dx. Pretty simple. Then we need to add this middle one, which we'll come back to. So let's get to this one first. First of all, this 7 is a constant that can be pulled out to the front. So we're going to add 7 times the antiderivative of 1 divided by x squared dx. Just like an example we did earlier, the antiderivative of 3 to the x, remember this was a constant. It's the same concept here. So this changed into 3 times the antiderivative of 1 over x. It's the same concept here, except of course with a 7 and an x squared. Now let's do this middle one. This one's a little bit more complex because it doesn't divide evenly like our first antiderivative. So I'm going to bring this over and do a little bit more work down here in this area. Let's draw an arrow over here. X to the 1/4 divided by x squared can be rewritten. Whenever we have a negative exponent, that means we take a function with a power to it and bring it to the wrong side of the fraction. So in this case, we have x squared on bottom. If we were to bring this to the top, then it would be -2. But it would be equal to the same thing. It's just on the wrong side of the fraction. Let me write it down so that way this all makes sense. This is now x to the 1/4 times x to the -2 power. See how we took it to the numerator and then flipped it to a negative? That's what we did here. Another trick with exponents is that if they have the same base and are being multiplied, then we can add their exponents and make it one function. In this case, we do have the same base of just x. So we can change this into x to the 1/4 minus 2, not plus, that is definitely a -2. And then this changes into x to the -7/4 power. So our middle function is the antiderivative of x to the -7/4 power dx. Don't forget your dx, it's very important to remember to write that. Okay, now that we're at this step, we can actually solve all of these using the power rule for antiderivatives. Let's first do the easiest function. Remember, whenever we're taking the antiderivative of a function to a power, we can use the power rule for antiderivatives. So that rule states that we have to add 1 to the exponent, so in this case it'd be x to the 2 plus 1 power, and then divide it by this. So x to the 2 plus 1 divided by 2 plus 1. Now let's do our second function. We can apply the exact same rule here, except it's a little bit more of a funky number. Let's write that down here as x to the -7/4 plus 1 divided by -7/4 plus 1. Now our last one, we need to multiply 7 by the antiderivative of 1 divided by x squared. So let's write 7 down here first. It'll be plus 7 times this antiderivative. Now 1 divided by x squared is equivalent to x to the -2 power, and that's much easier to work with. So let's take the antiderivative of x to the -2 power. That turns into x to the -2 plus 1 divided by -2 plus 1. Now we're almost there. We just need to simplify all these functions down. Of course, x to the 2 plus 1 is equal to x cubed, all divided by 3, plus, now our middle function, -7/4 plus 1 is the same thing as -7/4 plus 4 over 4. So we add -7 and 4, and that gives us x to the -3/4 power, all divided by -3/4, plus the last one here, plus 7 times x to the -1 power divided by -1. Now we're going to simplify down this one just a little bit because it looks bad. First of all, we can multiply the 7 and it would just have a 7 on top. But you may also notice that we have an x to the negative first power. Since it has a negative exponent, that means it's on the wrong side of the fraction, and we can move it and make it look a little bit nicer. So this function, I'm going to erase what I have here, or actually no, I'll just do this. Now it turns into 7 divided by x, negative 7 divided by x specifically. So let's just bring everything down so it looks nice and neat. I'll erase this arrow and draw a new one over here. This turns into x cubed divided by 3 plus, let me get my green, x to the negative 3 fourths divided by negative 3 fourths plus, and then, or I should say minus, since this is a negative 7 to the x. Instead of writing plus and negative, I'll just write minus. Minus 7 divided by x, and then of course at the end of all of our antiderivatives, we just add c. So this is the answer. It took a few more steps and a little bit of algebraic manipulation, but it's good to get used to this stuff because some of these exponent tricks especially will come in handy later in calculus and just later in math in general. Knowing these tricks is very helpful for solving stuff like this. Now that we've done a couple examples, let's go over a few more rules of antiderivatives. In fact, they're all rules about trig function. Hang in there with me, we're gonna have to write a lot of them down, and it does take a second to memorize all of them, but once you do, it makes solving antiderivatives much easier. So let's do that now. The antiderivative of sine of x dx is equal to negative cosine of x plus c. Always remember your plus c. I'm going to write plus c on all these examples. I need to hammer it into your brain. Always put this plus c at the end of your antiderivatives. It's very important. Next up, of course, we have the antiderivative of cosine of x dx, which is equal to sine of x plus c. Like I've emphasized during this video, antidifferentiation just takes your derivative and finds the original function. The derivative of sine is cosine, the antiderivative of cosine is sine. Next up we have the antiderivative of secant squared x, and this is equal to tangent x plus c. The antiderivative of cosecant squared x is equal to negative cotangent of x plus c. Now those are all the ones that are a little bit easy to remember. Let's get into the weird ones now. Oh, and I apologize. I didn't write dx here and here. I know, I'm the one teaching you, and I emphasize that you need to write dx every time. Please write dx at the end of all of them. You will need that later on whenever we do more antidifferentiation and make it more complex. Sorry, that's my bad. Always write your dx at the end of your antiderivatives. Let's write it up here just so we get in the habit. And this is equal to negative cosecant x plus c. I'm on the very edge of my board here. Okay, now let's get the really weird ones out the way. The antiderivative of 1 divided by 1 plus x squared dx is equal to arctangent of x plus c. This is also equivalent to inverse tangent, tangent negative 1 of x. This is the same thing. I just want to make that distinction very clear. Next up, we have the antiderivative of 1 divided by the square root of 1 minus x squared dx, and that one is equal to arcsine of x plus c. Once again, this is equivalent to inverse sine, just like inverse tangent up here. The antiderivative of secant x tangent x dx is equal to secant x plus c. All right, and the last one, and easily the weirdest one, the antiderivative of 1 divided by the absolute value of x times the square root of 1 minus x squared dx is equal to arcsecant of x plus c. I know this one's very weird, but it just equals arcsecant, so don't worry about actually doing all the math. Just remember that. Okay, but what are we actually using antidifferentiation for? Obviously, you can take the derivative and find the original function, but it has one more, way more interesting and way more powerful use. Let's talk about that now. The one really cool thing about antidifferentiation is this. Let's say we had a graph, I don't know, something like the x squared graph, that positive parabola we've seen since algebra. Let's draw it with blue. Let's draw it with red. Okay, man, let's draw it with red, just for fun. We have the positive upward-facing parabola of y equals x squared. What if I wanted to find the area under the curve? Let's say the area under the curve between 2 and 0. This area here. Let's shade that in with blue that I dropped on the floor just a second ago. This area here. What if I wanted to find this area? Well, here's the hard part. Obviously, we don't have a formula for that exact shape. Or say we had some random arbitrary function like this, and I wanted to find the area under this curve, like so. We don't have a function to just find that. It's not like a rectangle where we just multiply length and width, or a triangle 1/2 base times height, so on and so forth. So how will we find the area under here? We can use antidifferentiation for that. You see, whenever we take the antiderivative of something, this is also known as taking the integral of something. I know, big reveal here. Antiderivatives are also known as the integrals of a function. Let's say we had a function that looks something like this. I don't know, we wanted to find the antiderivative of 2x dx. As we've talked about extensively, this is equal to x squared plus c. We can also word this as the integral of 2x dx is equal to x squared plus c. This elongated s here is known as an integral, and whenever we take the integral of a function, it has two very nice things. One, and the obvious one, we've been taking antiderivatives, which means if we are given the derivative of a function, we can find the original. But the other really nice one is that it'll give us a function that can tell us the area under a curve, or maybe even more impressively, between two curves. Let's say we had a curve like this, and we wanted to find only this area here, between these curves. We could find the area between those two curves using integrals. Now, that's way beyond this lesson, but I do want to mention that's what integrals are for, and that's why I think they're really, really cool. But first, let's find the area under a curve. Not this one, because we've been using x squared all video. Let's do something totally different, like x cubed. Okay, let's draw a graph here. We'll draw the graph with green, and we're going to just simply draw the x cubed function. Something like this. It looks something like that. I'll denote this as y equals x cubed. And I want to find the area underneath this curve between the points 2 and 0, just like before. So, you know, this area here. And we'll shade that in with blue just to make that very distinct what we're looking for here. As noted a minute ago, we don't have a function that can just tell us this area. It's not a square, it's not a rectangle, it's not a circle. It's not something easy. It's a weird shape that we don't have a definite function for. So let's use some antidifferentiation, or the integral of this function, in order to find the area underneath this curve between those 2 points. So what we need to do is find the antiderivative of x cubed. So the integral, or the antiderivative, this is an integral symbol. You can call it an antiderivative. Most of the time I say the integral of a function is equal to, but you can say either one and people will know what you mean. So I'm going to say the integral of x cubed dx. And remember, we can just use the power rule for integrals. I know I've been saying the power rule for antidifferentiation, but from now on, I'm probably going to refer to this as the power rule for integrals. That's to differentiate it from the power rule for differentiation. Another calculus pun for you. Anyway, let's use that power rule. We can take x, and then we just have to add 1 to its original power, 3 plus 1, and then we just divide it by 3 plus 1. So this is equal to x to the 4th divided by 4, plus c. Don't forget your plus c. Very important to remember. So what's the area underneath this curve? The area at 0 is equal to 0 to the 4th divided by 4. I'm going to denote that as at 0. 0 to the 4th divided by 4, which of course is equal to 0. At 2, this area is equal to 2 to the 4th power divided by 4. 2 to the 4th power is 2 times 2 is 4, times 2 is 8, times 2 is 16. So this is equal to 16 divided by 4, which of course is equal to 4. So the area underneath the curve of x cubed between 0 and 2 is 4 units, whatever your unit might be, or just 4 for simplicity's sake. Now we'll talk about this specific area whenever we start talking about definite integrals, but that's for a much further on lesson. For now, I just want to introduce you to antidifferentiation, and surprise, I'm actually introducing you to integrals. I hope you enjoyed this video today. If you did, consider subscribing, and if you're ready to learn more calculus, consider checking out the Calculus 1 playlist linked here. I'll see you guys in the next video.